Sometime in the mid-1990s, a decision was made in a boardroom that had nothing to do with engineering. No metallurgist was consulted, no stress test was run. A marketing team, working from a cost of ownership spreadsheet, decided that the cars they were selling needed to feel less demanding. Buyers were comparison shopping. Rival brochures promised sealed gearboxes and 10,000-mile oil intervals. The message was simple. Our cars are so advanced they barely need you. The engineers in the room knew it was not true. The fluid sealed inside those transmissions was never designed to last the life of the car. It was designed to last long enough. Long enough for the warranty to expire. Long enough for the liability to pass to the next owner. The accountants called it progress. The engineers called it nothing because nobody asked them. That decision quietly set an expiration date on the greatest cars ever built. Between 1990 and 2005, the automotive industry produced machines designed to outlast their owners. They are disappearing now, and the people who built them knew this would happen. To understand how these cars are dying, it helps to understand what made them extraordinary in the first place. The late 20th century was a singular moment in industrial history. Computing power had finally caught up with engineering ambition, giving designers tools to simulate tolerances and stress loads that previously required years of physical testing. But old-world craftsmanship was still the dominant philosophy inside the factories. The people building these cars had grown up in an era where materials were chosen for permanence, not for cost reduction. For one brief window, those two worlds overlapped perfectly. Companies like Mercedes-Benz and Lexus operated under a directive that sounds almost irrational today. Build the best machine possible. Figure out the price later. Cost does not matter. Perfection, not profit. That was the mandate, and engineers took it seriously in ways that are difficult to fully appreciate now. The Lexus LS 400 arrived in 1990 and immediately embarrassed every German manufacturer it competed against. Toyota had spent $300 million developing it, deploying over 1,400 engineers across 60 design teams. The engine produced silky, near-silent power from a 4-liter V8 that was balanced to tolerances once reserved for aircraft components. A coin placed on the running engine would sit perfectly still. That was not a party trick. It was evidence of the obsessive rotational balance engineered into every moving part. The Mercedes W140, launched in 1991, approached the problem from a different angle, but reached the same conclusion. Its body shell was engineered with a structural rigidity that made contemporary competitors feel hollow by comparison. The chassis absorbed road noise through a system of subframes isolated from the body by thick rubber mounts, keeping the cabin tuned for silence even at autobahn speeds. The climate control dials had a specific calibrated resistance, not too loose, not too stiff. Engineers tested them until the tactile feedback communicated quality, not just function. These details matter because they reveal the philosophy behind the engineering. The teams building these cars were not just solving mechanical problems, they were making statements about what an automobile could be. Thick-gauge steel, real wood veneers sourced and matched by hand, suspension components tested to tolerances far beyond any practical requirement. These were machines built to last not just years, but decades. And for their original owners, they did exactly that. A surgeon who bought an LS 400 in 1990 and maintained it properly might still be driving it today. The engineering was genuinely that sound. But original owners eventually move on. They trade up, they retire, or they pass away, and the car filters down through the market. By the time a W140 reaches its third owner, it might be worth $4,000. The person who buys it at that price is not necessarily equipped to maintain a machine that was built to a standard most modern mechanics have never encountered. They are accustomed to modern economy features that tolerate neglect, that send warning lights weeks before anything actually breaks, that are designed for a world where maintenance is an inconvenience rather than a discipline. That gap between how these cars were built and how they came to be treated is where the DIYing begins. The metal did not give up. The engineering did not fail. The culture around the cars simply forgot what they required, and the manufacturers, it turns out, helped that forgetting along. The first fatal blow to these over-engineered machines did not come from a pothole or a failed bearing. It came from a marketing department. As the late 1990s approached, the luxury automotive industry faced a problem. Buyers were comparing total cost of ownership, and the rigorous maintenance schedules these cars demanded were making them look expensive to live with. A Mercedes-Benz that needed transmission fluid every 30,000 miles felt like more work than a competitor promising sealed-for-life components. So, the accountants made a decision, and the engineers were told to find a way to justify it. The lifetime fluid was born. It was a fiction dressed up as progress. Marketing departments began advertising 10,000-mile oil change intervals and sealed-for-life gearboxes as evidence of engineering advancement. BMW was among the most aggressive, promoting extended service intervals on the E39.5 series as a feature, not a compromise. The message to buyers was straightforward. This car is so sophisticated it barely needs attention. The reality was something else entirely. Lifetime, in the language of an automaker's legal department, means the length of the factory warranty. Nothing more. The fluid sealed inside a transmission at the factory was never expected by its engineers to last the life of the car. It was expected to last long enough that the manufacturer's obligation ended before the damage began. The second owner, the third owner, the person who bought the car at 70,000 miles from a rental fleet, they inherited a mechanical time bomb with no visible fuse. Heat is the primary enemy inside a modern automatic transmission. These gearboxes operate at temperatures between 175 and 220 degrees Fahrenheit under normal conditions. Every 20 degrees above that range cuts the fluid's protective lifespan roughly in half. The clutch packs, the valve bodies, the planetary gear sets, they all depend on clean fluid maintaining a precise film of lubrication between moving surfaces. When the fluid breaks down, that film thins. Metal begins to contact metal. The debris from that contact circulates through the system, accelerating the damage exponentially. A gearbox in an E39.530, engineered to the same demanding tolerances as the rest of that car, built to last 400,000 miles under proper care, can fail completely at 150,000 simply because nobody changed the fluid. The gearbox didn't wear out. It was starved. The fine clutch material that should have lasted decades instead turned to abrasive paste and destroyed the valve body from the inside. The engine block suffered the same fate through a different mechanism. Extended oil intervals allowed carbon and sludge to accumulate in passages that had never been designed to tolerate contamination. The variable valve timing systems introduced on engines, like BMW's M54 and the Lexus 3-liter inline-6, relied on clean oil pressure to actuate their solenoids precisely. Sludge choked those passages. Timing responded erratically. Owners reported rough idle and poor throttle response, replaced sensors and solenoids, and never found the root cause because the real problem was invisible, coating every internal surface in a thin film of neglect. The cruelest irony is that the owner's manual became the instrument of destruction. A buyer who followed the manufacturer's printed guidance exactly, who did everything right by every official measure, was unknowingly killing the machine. The service intervals written into those manuals were calculated against warranty expiry dates, not engineering tolerances. Compliance meant slow, invisible damage accumulating over years until something catastrophic made the problem undeniable. By then, the repair bill was enormous, and a car worth $4,000 on the open market didn't justify a $3,000 transmission rebuild. In the mind of an owner who hadn't been told it was coming, the fluid dried up, the gearboxes gave out, and the forever cars left the road one sealed transmission at a time. While the marketing departments were quietly starving the drivetrains of clean fluid, a different kind of destruction was taking hold inside the engine bays of Europe's finest cars. This one did not come from neglect. It came from good intentions, from a genuine desire to do something responsible, and the results were devastating. In the early 1990s, European manufacturers came under increasing pressure from environmental regulators. The new directives were clear. Vehicle components had to be more recyclable. End-of-life disassembly had to be cleaner, simpler, and less toxic to process. The intentions behind those regulations were sound. The automotive industry generated enormous volumes of difficult-to-recycle materials, and reducing that burden was a legitimate engineering goal. Mercedes-Benz responded by making a change that seemed reasonable on paper and proved catastrophic in practice. The wiring harnesses running through the W124 and the W140, the complex nervous systems carrying signals to every sensor, actuator, and control module, were wrapped in a biodegradable insulation material. The compound was designed to break down cleanly at the end of the vehicle's life, making recycling easier and reducing environmental impact. The engineers who approved this decision were thinking about the car's final years in a recycling facility. They were not thinking about what happens to biodegradable material when it spends a decade sitting inches from a running V8 engine. Heat is patient. It works slowly and without announcement. An inline six running at normal operating temperature generates sustained heat in the engine bay that never fully dissipates. Every time the car is driven, the harness absorbs that heat. Every time the engine cools overnight, the harness contracts. This cycle, repeated thousands of times over 10 years, accelerated exactly the chemical process the insulation was designed to eventually undergo. The breakdown that was supposed to happen 30 years later, in a controlled recycling environment, began happening in driveways and parking garages and highway lanes across Europe and North America. The insulation turned brittle. It cracked. Then it crumbled. In some cases, it did not crumble at all, but simply turned to a fine dust that fell away from the copper conductors it had been protecting. What remained was a network of bare wires running through an engine bay filled with metal surfaces, heat sources, and vibration. Short circuits became inevitable, and the symptoms that followed were baffling. A car built like a bank vault would suddenly develop an erratic idle for no apparent reason. A W140 with a structurally perfect chassis and a mechanically sound engine would refuse to start on a cold morning, or throw a cascade of unrelated fault codes, or, in the worst cases, develop an electrical fire in a harness buried deep under the intake manifold. Mechanics unfamiliar with the specific failure mode would chase sensors and modules for weeks, replacing parts that were not broken, because the root cause was invisible until you looked closely at the wiring itself, and found it had simply ceased to exist as insulation. The economic math was brutal. A full wiring harness replacement on a W140 required hundreds of hours of labor, navigating a system that Mercedes had engineered to an exceptional standard of complexity. The parts alone could exceed $2,000. The total repair at a competent independent workshop could push $4,000. On a car with a market value of $5,000, that calculation destroyed the vehicle as surely as a collision would. Owners faced a choice with no good options. Spend nearly the entire market value of the car on a repair that addressed one failure while leaving other potential issues unresolved, or send a mechanically perfect automobile to the crusher because its wiring had dissolved. Most chose the crusher. The accountants, without meaning to, had built their own kind of planned obsolescence into the harness of every car they ever claimed would last forever. The wiring harness failure was a betrayal of philosophy, a case where good environmental intentions produced mechanical catastrophe. But the next wave of destruction came from something more straightforward. It came from cost reduction dressed up as material science, and it killed more engines than any wiring fault ever could. For most of the 20th century, cooling systems were built from materials chosen for one reason above all others. They had to survive. Brass and copper radiators, cast aluminum housings, thick rubber hoses reinforced with braided fiber. These were components selected because engineers understood that a cooling system failure did not mean a repair bill, it meant a destroyed engine. The consequences of getting it wrong are so severe that the materials were overspecified deliberately, given margins that absorb decades of heat cycles without complaint. A brass radiator from a well-maintained 1978 Mercedes could outlast the body it sat in. That was the point. Then, Somewhere in the mid to late 1990s, a calculation changed. Composite plastics had become sophisticated enough to handle moderate thermal stress. They were lighter than metal, and crucially, they were cheaper to manufacture at scale. Engineers began replacing metal cooling components with plastic ones, component by component, starting with the pieces most buyers would never think to inspect. Thermostat housings, expansion tanks, water pump impellers. The parts that touched coolant directly but sat out of sight behind intake manifolds and beneath coolant hoses. BMW E39.5 series and the P80 generation Volvos became the defining case studies in what followed. Both cars were genuinely excellent machines, built with real engineering integrity across most of their systems, but their cooling systems were essentially countdowns. The plastic expansion tanks on the E39 were notorious. The plastic thermostat housing on the Volvo 5-cylinder engine failed, with a regularity that became a dark joke in ownership forums. Not because these components were poorly designed in isolation, but because plastic and sustained thermal cycling are fundamentally incompatible over the long term in a way that no amount of polymer engineering can fully resolve. The physics are straightforward. Plastic expands when it heats and contracts when it cools. Every single drive cycle puts the material through that stress. Over 2 or 3 years, the cycling is tolerable. Over 10 years and 100,000 miles, the cumulative fatigue builds invisibly inside the material structure. No crack appears on the surface. No weep develops that might alert an attentive owner. The component simply holds its shape right up until the moment it does not, and when it lets go completely. A metal expansion tank that begins to fail develops a seep. Coolant appears on the outside of the tank, collects on the underside of the hood, leaves a dried mineral residue that an owner notices during a routine check. There is time to respond. A plastic expansion tank that reaches the end of its fatigue life can split along a seam in an instant, draining the entire cooling system in minutes at operating pressure. The temperature gauge climbs, the owner pulls over or does not. Either way, the aluminum cylinder head on an engine that was built to last 300,000 miles begins to warp within minutes of losing coolant at operating temperature. Aluminum warps quickly because it conducts heat so efficiently. The same thermal conductivity that makes it an excellent engine material becomes its vulnerability the moment coolant stops flowing. A head that costs $1,100 to machine and another $800 to gasket properly is destroyed by the failure of a $50 plastic component that any knowledgeable owner could have replaced preemptively. The E39 with the warped head goes to the salvage yard. The Volvo with the cracked thermostat housing sits in a driveway, accumulating leaves. The engines inside both cars are, mechanically, almost perfect. The block is fine. The crankshaft is fine, the gearbox is fine, none of that matters now. A $50 part made the decision for everyone. There is a pattern running through every failure covered so far. The wiring harness dissolved. The transmission fluid turned to sludge. The plastic expansion tank split without warning. In each case, the engineering itself was sound. The ambition was genuine. What killed these cars was a mismatch between how they were designed and how they were eventually cared for. The suspension systems fitted to the flagship luxury cars of this era follow the same arc, but the economics of failure are even more punishing, and the cars that suffer most are some of the most remarkable machines the period produced. The pursuit of a perfectly isolated ride was one of the defining obsessions of the 1990s luxury engineering. Passive steel springs and conventional shock absorbers had been refined to a high standard by that point, but they had a fundamental limitation: they could not adapt. A spring rate tuned for comfort on a smooth highway felt floaty on a winding road. A stiffer setup that handled well made the cabin harsh over expansion joints and broken pavement. Engineers wanted both, and they were given the budgets to chase it. The solution was active and semi-active suspension. Hydraulic systems could alter damping in real time. Pneumatic air struts adjusted ride height based on speed and load. Height control systems kept the body level regardless of how many passengers climbed in or how much weight sat in the boot. When these systems worked, and when they were new, the result was genuinely astonishing. The Toyota Land Cruiser 100 series with active height control felt like it was reading the road ahead of the wheels. The Lexus LS 400, riding on electronically controlled air suspension, absorbed imperfections with a composure that felt closer to a private aircraft than a motor car. These were not marketing claims. They were real engineering achievements, delivering a quality of ride that no conventional suspension could match. But rubber does not last forever, and compressed air is only as reliable as the bladders and seals containing it. Air suspension bladders are made from reinforced rubber compounds, designed to flex millions of times across decades of service. They tolerate heat, cold, ozone exposure, and the constant cycling of inflation and deflation. For the first decade, they hold. Then, gradually, the rubber stiffens and cracks at the flex points. Small leaks develop. The compressor runs more frequently, trying to maintain pressure against a system that can no longer hold it. Eventually, the compressor itself fails from overwork, and the car settles onto its bump stops overnight, sitting nose down or lopsided in the driveway every morning, until the owner manually inflates the system just to drive it. The hydraulic systems fitted to some Mercedes and Citroën-influenced designs had their own failure points. Pump seals dry out, fluid oxidizes, accumulator spheres lose their nitrogen charge. The system that once transformed body motion into something serene becomes slow, reluctant, and eventually inoperative. The repair costs are not modest. A full air suspension overhaul on a Land Cruiser 100 series, replacing all 4 struts with quality components and addressing the compressor and height sensors, runs close to $4,000 at an independent workshop. On a car that a third owner purchased for $5,000 or $6,000, that bill is existential. It does not just strain the budget, it forces a decision about whether the car has a future at all. Most owners do not make the repair. Some convert the system to passive springs using aftermarket kits, which solves the reliability problem while erasing the ride quality that justified the engineering in the first place. Others simply drive the car in its degraded state, the chassis sitting lower than it was designed to, stressing geometry and wearing tires unevenly, accelerating damage to components that were perfectly healthy before the suspension collapsed around them. The system that defined the car's character becomes the reason the car is abandoned. Every failure described so far shares a common thread: complexity. The biodegradable wiring was complex. The sealed transmissions were complex. The plastic-laced cooling systems were complex. The pneumatic suspensions were extraordinarily complex. European and Japanese luxury engineering of this era operated on the belief that refinement required layering system upon system. They solved each new problem with a more sophisticated solution, until the car became something only the manufacturer's own dealers truly understood. That philosophy produced machines of genuine brilliance. It also produced machines that could not survive the slow drift from attentive first owners to budget-conscious third owners, with a local independent mechanic and a limited parts budget. American engineering took a different view entirely. The Ford Panther platform is not a glamorous subject. Nobody writes reverent essays about the Crown Victoria's drag coefficient or the Lincoln Town Car's interior sound-deadening philosophy. These were not cars that embarrassed the Germans or unsettled the Japanese. They were not trying to. The engineers who developed and refined the Panther platform across its production life from 1979 through 2011 were solving a completely different problem, and their solution was almost philosophically opposed to everything happening in Stuttgart, Munich, and Nagoya. The directive, stripped to its core, was durability through simplicity. Heavy body-on-frame construction, borrowed from truck engineering, meant the body panels could rust, dent, and be replaced without compromising structural integrity. The chassis underneath simply continued doing its job. The 4.6-liter V8 fitted to Crown Victorias and town cars was a large displacement, low-stress engine by any measure, producing modest power relative to its size, and running well below its mechanical limits under normal driving conditions. An engine that is never working hard is an engine that is not wearing quickly. The engineers understood this, and they built accordingly. There were no biodegradable wiring compounds, no sealed-for-life gearbox promises, No plastic cooling components hiding behind intake manifolds, waiting to fail at speed on an interstate. The cooling system was metal. The transmission fluid was accessible and serviceable through a conventional dipstick. The suspension was conventional double wishbone geometry up front with a live rear axle, heavy, simple, and almost impossible to kill through ordinary neglect. Taxi fleets in New York and Chicago drove these cars for over 500,000 miles on basic maintenance alone, returning them to service day after day across years of continuous operation. Police departments ran Crown Victorias as patrol cars because the platform could absorb punishment that would have destroyed anything built to European luxury standards. There is a certain humility to that kind of engineering. It does not ask for admiration. It does not deliver a floating sensation over broken pavement or a vault-like door thud that communicates premium intent. What it delivers is the same reliable experience at 200,000 miles that it delivered at 20,000, because the components asked to do that work were never particularly stressed in the first place. But even the Panther platform is disappearing, and its disappearance proves something important. These cars are not dying because the engineering failed. Ford discontinued the platform in 2011, not because the Crown Victoria wore out, but because the market demanded touchscreens, fuel economy figures that required lighter construction, and technology that could not be grafted onto a chassis designed in another era. The taxi fleets that kept these cars running past 500,000 miles did not abandon them because they stopped working. They abandoned them because city regulators began requiring accessible vehicles, and because passengers wanted the experience of riding in something newer. The Panther platform was killed by culture, not by mechanical failure. And if the simplest, most indestructible platform of the entire era could not survive a society that stopped valuing permanence, what hope remains for the complex, demanding masterpieces built alongside it? So the question becomes a practical one. The Panther platform is gone. The W140 is 30 years old. The E39 is being crushed for scrap at a rate that should alarm anyone who understands what is being lost. But the cars that remain, the ones still running, the ones sitting in garages under dust covers or commuting quietly on back roads, those cars can still be saved. Not by nostalgia, not by sentiment, by maintenance, done the way these machines were designed to receive it. Keeping one of these cars on the road requires a conscious decision to reject the habits the modern automotive industry spent 30 years installing in drivers. The disposable mindset, the idea that a car is a subscription to be renewed every 5 years rather than an object to be understood and preserved, is the single most dangerous thing an owner of a 1990s or early 2000s masterpiece can carry into their garage. Reject the disposable mindset. Start with the fluids, because the fluids are where most of these cars are lost. Ignore the factory service intervals completely. Change the engine oil every 3,000 miles with a quality full synthetic appropriate to the engine's specification. Flush the transmission fluid every 30,000 miles, regardless of what any sealed for life language in the manual suggests. Treat the coolant as a wear item, not a permanent fill. Drain and replace it every 2 years because old coolant turns acidic and begins attacking aluminum from inside the passages no visual inspection can reach. Brake fluid absorbs moisture from the air every single day it sits in the system. Flush it every 2 years before the boiling point drops far enough to compromise the pedal under hard use. Then address the plastics before they address themselves. Every P80 Volvo still on the road needs a new thermostat housing and expansion tank installed new, not after the original one splits on an interstate. Every E39 needs its coolant expansion tank and water pump inspected at every service interval. A $50 part replaced during a routine oil change is an investment. The same $50 part replaced after it fails costs an engine. The arithmetic is straightforward, but it requires an owner who is thinking about the car as an object worth protecting rather than a machine to be used until it breaks. For the Mercedes with the crumbling wiring, the path is harder but still achievable. The repair is expensive. There is no honest way to frame it otherwise. But a full wiring harness replacement on a W140 or a W124 returns the car to a better electrical state than it left the factory in, because modern replacement harnesses use conventional insulation that will not dissolve. That repair, properly done, should last the rest of the car's life. The question is whether an owner values the machine enough to make the investment. And if the machine is a structurally sound, over-engineered masterpiece built during the brief window when budgets were unlimited and accountants had not yet taken the steering wheel, the answer should be obvious. The suspension systems deserve the same honest accounting. Air bladders are available as aftermarket components. Compressors can be rebuilt. The cost of maintaining a properly functioning hydraulic or pneumatic suspension on a Land Cruiser or an LS 400 is real, but it is not infinite. What is required is the willingness to spend on maintenance the way the original development team spent on engineering. They did not cut corners when they built these cars. Cutting corners when maintaining them is a betrayal of everything that made them worth owning. Listen to the machine. A worn engine mount transmits a specific vibration before it misaligns the drivetrain. A cooling system losing pressure shows it in the overflow reservoir before it shows on the temperature gauge. These cars communicate clearly to anyone paying attention. Pay attention. The automotive industry will never again build machines with this level of intentionality, heft, and soul. When the last of these over-engineered legends goes to the crusher, that philosophy of permanence disappears with them. If you remember the vault-like thud of a real car door, tell me your favorite design detail from this era in the comments below. Subscribe if you appreciate the true craftsmanship of the past.